name is Eugene. So today we want to continue our discussion about gravity. Specifically, how do we shield against gravity? In previous videos, we discussed the nature of reality as well as the nature of gravity. So in this video, I want to go over how we can shield against gravity. So that will allow us to give us an anti-gravity effect where we can shield against the updraft of gravitational particles and essentially have our anti-gravity device float on the updraft of particles. So as described earlier, right, so the idea is to have a craft and to build a barrier around the craft and this barrier would essentially consist of gravity particles. So the same particles, if this is the planetary surface, then we have a downdraft of gravity particles. As explained in my previous videos, so go ahead and take a look at those to get a better understanding. But essentially we have a downdraft of gravity particles towards the center of the planet, and once they get to the center of the planet, pressure builds up, and then we have explosion of gravity particles, essentially high energy explosion of gravity particles that rips through everything. So when it encounters matter, it doesn't, it essentially just, flows right through the matter. So the way gravity works, if you have matter, then if matter is caught in this gravity field, the gravity particles filter through this object and essentially drags it along. So it's a physical interaction of the gravity particles with matter. So the question is, how do we build this barrier? Is it even possible? What is the mechanism of building this barrier? As I've stated earlier, this barrier would consist of gravity particles. So in other words, these particles would essentially serve as obstacles for the downward movement of these particles. So essentially the downward draft would then bounce off these gravity particles. So we'd have to build a really thick or dense barrier around this craft. So if we take a closer look at what that looks like, so if we look at let's look at the so this is a representation of the hull of the shell of the craft. So you'll have some sort of metal, right? It has its molecules, atoms, whatever. And as these gravity particles filter through this metal, it interacts with, at the atomic level with the material itself, and therefore cause a drag effect in the direction of the flow of the gravity particles. So this flow doesn't necessarily have to go, doesn't necessarily have to be downwards. It just has to, there just has to be a flow in any direction. But typically close to a planet, the direction would be towards the center of the planet. So the idea then is to, as this metal gets charged with these gravity particles, or as the gravity particles filter through this hole, the skin of the crab essentially. So as it filters through it, the idea is then to, by some mechanism, expel all these particles contained in the material, expel it outwards so that they form a barrier on the outside of the skin. By doing so, they impede the downward or the incoming gravity particles and cause the gravity particles to flow around the skin of craft. So the question now is, how do we do that? Okay. First of all, let's revisit what a gravity particle is. So, as explained before, right, we have the universal bubble, and in this universal bubble we have a single particle, and this single particle it's the only particle in the universal bubble, so it has infinite velocity and essentially bounces off the boundaries of this universal bubble. So in order to observe reality, we essentially have some sort of instrument that we are able to tune it to certain frequencies, and the frequency or its vibration essentially means it's on or off, and typically, when it's on and the particle is within the region of that instrument, the particle it becomes observable. And this instrument has a certain frequency, a very short interval. So during that interval, it essentially observes where the particle is. So whenever the particle is within the instrument, it registers the structure. So the more a particle is observed in the same position, meaning it's crossing that same position many times, we observe more of that particle, so the structure becomes more solid. Right? So if we had to observe one of these molecules or atoms, we'll essentially would have to observe the particles traversing many times in a small location, and whenever it crosses, that represents a particle. So in this case, in the center of this cloud of particles, we'll have a denser cluster. So that represents the atomic nucleus, and in the surrounding area of that nucleus, we have a particle cloud of various different particles. So we know that if we start smashing atoms together, or smashing particles together, they always break into smaller and smaller particles. So the idea then is that the protons and neutrons, they're really a cluster of particles. Similarly, the electrons around the nucleus, they also consist of the nuclear electron cloud around the nucleus, also consists of many different particles. So it depends on how many times that particle crosses in that location, and also at what frequency it crosses. And so what this means is then if we have gravity particles, flowing through, and you have several atoms, and if these gravity particles flow through or filters through the matter, it encounters particles that are similar in nature to these gravity particles. And when it does that, so they're similar because they have the same frequency, or they are rendered in a similar fashion. So when it encounters these particles, it bounces around. So it bounces off that particle, and maybe it meets another particle, bounces again. So in that respect, in another gravity particle comes down and also bounces off that particle. So there's like a filtering effect or dragging effect where the gravity particles struggle to go through the material. So in that respect, because of the pressure of the other particles coming down, it also drags the matter along with it. So then this gravity field, or this gravity flow, or gravity particle flow, then drags everything along, in its path, because of this interaction with particles within the atomic structure. So we know that gravity affects all observable matter, essentially. So that means this particular particle it interacts with is contained in all matter. So it even affects the passage of light. So if light encounters a gravity field, it is also bent by the gravity field. We know this because if we look at, for instance, around a black hole, we essentially observe that light is trapped within the black hole. Also, we know that when we look at stars through a telescope, then we can also see the light bend as well in that respect. So gravity does affect light particles as well, though. So even at that smallest level, the light particles has to consist of that same or similar particle, as a gravity particle. So given that, my assumption then is that this gravity particle is very similar to magnetic particles. We know that magnetic particles, all matter essentially contains these magnetic particles. We also know that in various experiments throughout the years, we've seen the relationship between magnetic particles, electric fields, and gravity. We've also seen, many reports of people doing experiments with strong magnetic fields, rotating magnetic fields, and they observe that it affects gravity. So in that respect then, these gravity particles represent magnetic particles, right? But they're not really magnetic in the sense of a magnet. And the reason that is because if you have a magnet, as I described before, right, in the magnet we have these atoms, and this atom or the electron um, field or cloud around this atom or nucleus has a certain frequency, meaning as it pulses or vibrates, that is essentially its frequency. I mean, later on we'll get into why things vibrate, why everything in the universe has a certain frequency, even at the atomic level. But essentially, so in the case of iron, these atoms have a certain frequency or a certain vibration, and at a certain as the particle vibrates, it emits a magnetic particle. And in unmagnetized metal or iron, it emits this particle in random directions. So it emits a particle, and then if a particle is emitted from this atom, it causes an imbalance or a vacuum or a lack of that particle. So it typically gets it from or absorbs the particle from another atom. So in this way, the magnetic particle flows within the metal itself. So there's no net magnetic flow, so the metal itself or the iron itself is unmagnetized. Also, if it cannot take on the particle of another atom, then essentially this particle tries to fill the void, and the closest void or inlet would be on the backside of that atom itself. So when we magnetize the iron, we typically place it in an external field, an external magnetic field, and now we align these atoms to all point in the same direction. Okay. Okay, so this is the important distinction, is that the atoms, they act like little pumps, and they're all focused in the same direction. So in the magnet, typically I have a north and south pole, or inlet and an outlet. So the magnetic particles flows out the one end and curves around and come back into the other end. So the magnetic effect then is because of these tiny pumps or atomic pumps that pumps the particle in one direction. So you have a very intense flow of magnetic particles close to the surface of the outlet or inlet. Now in the case of gravity, as I've explained, right, when you have your planet and you have these gravity particles or magnetic particles, they just the whole universal bubble is filled with these particles. So there's like a sea of these particles, and it represents like the background ether or medium that makes up the entire universe. So when you have a piece of matter within the sea of particles, okay, so in this case we have a planet. So this planet then represents an an absence of these particles, meaning there's a vacuum of these particles, because the matter itself, they take up space, so they essentially displaces this particle. Um, so because there's a vacuum, these particles try to fill this vacuum. So you have pressure, on this planet, and as these particles, you'll have then a flow of these particles trying to fill the void. So as they hit the boundary of this planet, they start encountering resistance. So they essentially get slowed down at the boundary. So then there's a buildup of these particles. Okay. So close to the surface there's a buildup of these particles. So it's like the magnetic particles get compressed towards the surface of the planet. So the density of these particles become higher. So that means when you're closer to this planet, you'll experience a stronger gravity drag effect. When if you're further away from the planet, the drag is not that great, and that's the reason why you have a stronger gravity pull or gravity drag, because of this compression of gravity / magnetic particles. So eventually these particles start to filter through the planetary body. And as they reach the center of this of the planetary body, there's no way for them to go, so they all start building up pressure. They try to escape because of particle crowding. They try to escape, but they can't. So pressure keeps building until a certain point where it gives, and we have a big explosion of these particles going out. And these are intense explosions. So where the incoming particles is a slow affair, where they filter down at a much lesser speed, while the outburst of particles is at a high velocity, and so instead of bouncing off these subatomic particles, they essentially just rip right through them or push them out of the way. So since they have higher momentum, they essentially just push these particles away and rips right through the matter. So we only get a magnetic effect if all these particles are flowing in the same direction. Now, in the case of gravity, they're not really flowing the same direction. I mean, they are flowing towards the same location, but not necessarily flowing in a coherent direction, so you don't have that magnetic effect. Okay. And we discussed that if we had to build a craft, so this craft then would have to shield from the downdraft and also has to shield from the updraft. And we can sort of balance on top of this updraft, and that would give us our anti-gravity effect. Because if you're in outer space, right, gravity, there's no real the effect of gravity is, is at a great distance, but the further you away from your gravity, or from any big planet, you'll experience less gravity flow. So the gravity particles would be back to its neutral state. In other words, there's no net direction. So you can shield yourself from these particles, but uh, how do you navigate? How do you move? How do you go somewhere? Because you cannot really push off these particles. All you can do is shield these particles, but there's no flow. But when you're close to the planet, you can go up, down, or depending on how you orient the field, right? You can move in different directions because of the drama that you have around the planet. But in deep space, there's no such drama. You may be able to find some gravity currents between a planet and its sun, or different planets, and you can ride that current, which is essentially just a flow of particles. So we need to figure out then, how we're gonna navigate, once we off the planet. But for the purposes of this series, we're gonna attempt to just produce something that will give us an anti-gravity effect, and then later on we can worry about that. Okay. Another thing we noticed that when we have current flowing within a conductor, let's say these are the atoms. And then when current flow, typically we have electrons flowing, right? And as the electrons flow, we notice that the flowing current produces a magnetic field around the conductor itself. So you have a spinning magnetic field around the conductor itself when the electrons flow. So it's almost like the conductor is inducing the same effect as a magnet, where this the iron metal has a natural tendency to emit magnetic particles, and if they're all aligned, we get the magnetic effect. In this case, let's say it's copper. So the copper, has this neutral state where you cannot magnetize it in the same way as iron. It's only when a current flows through it, you'll observe a magnetic field, and the field direction is in a circular pattern around the conductor itself. So why is that? So that also tells us that the magnet or the magnetic particles are closely tied, to the electron cloud, right? So in the case of iron, it gets emitted because of this the atomic structure has a certain vibration, and then it emits the particle. In this case, the electron jumps from atom to atom, so it essentially then disrupts the copper or the conductor atomic structures, which results in these atoms, which result in these magnetic particles being emitted, right? So let's take a closer look at that. So let's say we have one of these conductor atoms, and when an electron jumps, to that atom, and there's essentially a lot of electrons, which represents the current, right? So that is the atom. So what happens then is that this electron gets absorbed by that atom. This atom's frequency changes, or its vibrational state changes, so it emits a magnetic particle, and then this particle, because of the electron flow, right, we have a dense electron flow, this particle gets expelled, and it's trying to find its way back into the metal or into the conductor, but typically we have the electrons flowing on the surface of the conductor, so it cannot find its way into, back into the metal itself. So that's the reason why it, just rotates around the metal, because it's trying to find its way into the metal itself. Another thing is when we have a capacitor being charged. So if the current flows this direction, right, if you have a flow of electrons this direction, and so this becomes positive and this becomes negative. So what happens is we have this, when this capacitor charges, right, we'll have magnetic current or magnetic particles rotating around this conductor, right? So as it, charges this plate, we see that as it charges this plate, we see that the this charging effect induces a motion of the capacitor towards the positive side. If you look at the work done by Townsend-Brown, or the Townsend-Brown effect, where they observed that if you have two charged bodies, one is negative and one is positive, and they are connected, and you rapidly charge, or you pulse the charging of this capacitor, you have movement towards the positive of the capacitor. So what is the reason for that, right? So let's take a look at what happens when you have a charged particle. What does that mean? So if you have a negatively charged particle, okay, so we know that when electrons flow, it causes the magnetic particle to be expelled, right? And essentially it cannot find its way back into the conductor, right? That's what's giving it its magnetic field. So when you charge this particle, the same thing happens where essentially pumping a whole bunch of electrons onto this particle. Similarly, you're also pumping a whole bunch of magnetic particles onto this particle. So in that respect, since you have an abundance of electrons, and they all push towards the surface of this particle. So what that means is then that you'll have these magnetic particles being pushed out again because of the crowding effect, because there's abundance of particles, abundance of magnetic particles as well as electrons. So these particles get all pushed out and they try to find their way back. Essentially, they'll orbit around this negatively charged particle, trying to find their way back. So this area then represents an area of high density of these particles relative to the background magnetic particles. Similarly, if you have a positively charged particle, what's happening here is, since it's lacking electrons, this represents a lack of magnetic particles. So in other words, you have from the surrounding sea of particles all trying to fill the void. It moves into this particle, and then it gets absorbed by the atomic structures within this particle. So as they get absorbed, they also get expelled. Since this charged particle essentially lacks excess electrons, there's an imbalance. So as soon as it absorbs the particle, the magnetic particles, it also expels them. Now again, the density of these particles is not even close to the magnetic particle, or in the case of a magnet, because it's all spread out, versus where you have a focused current essentially of these magnetic particles. So when you bring the positive and the negative particles, if you bring them close to each other, these orbiting magnetic particles, sees this positively charged particle as an area of void. In other words, there's a lack of these particles. So since it cannot find its way back into the negative particle, it takes the route all the way to that particle. And then when this particle is expelled, it finds its way back. So there's essentially a loop between these charged particles. This also results that they start attracting each other, because these particles creates a void essentially, and it tries to fill the void. So what happens then when in the Byfield-Brown effect, where you have a negative, let's say a negative sphere and a positive sphere, and they are separated, or they attach with some dielectric material. So when these, so when this capacitor is rapidly charged, so there's a sharp pulse where electrons are stripped from this sphere and added to this sphere. So if we look closely at what happens there, so suddenly this guy loses a lot of electrons, and they show up here, and immediately you have this cloud of magnetic particles swirling around this negative sphere, right? So when this happens, it immediately sees this as a area of attraction. So it then rushes over into that area to fill the void. And as it does so, there's a sharp pulse of these magnetic particles into this area or into this void. So whenever you have a pulse of these magnetic particles, they also induce motion in the surrounding magnetic particles or gravity particles. So that means the gravity particles also start moving in that direction. So in that respect, this entire apparatus or the apparatus or capacitor gets dragged towards the positive, or in the direction of the positive electrode. So that's essentially my understanding of the Bifield-Brown effect. So what does that mean for us? So this the Bifield-Brown effect is so represents the concept where we can essentially have some sort of artificial gravity. So if we have sharp charging or pulses between these plates, right, and then anything in between these plates would also be dragged along, because this causes a motion of the gravity particles towards the positive side of the plate. Now, of course, there's other geometries in terms of how you can structure this capacitor. Typically, you have a small positive area and a larger negative area, and this then creates different field effects. Typically, or the best example of this, where you have the so-called lifters, right? Where you have triangle-shaped capacitor, essentially. And if you look at just one of the side view of it, right? You have a big negative electrode, and then on top of that you have a wire, and that's charged positively, and this one is charged negative. So if you look at the field created by that, right, this is the typical field created by this configuration. So what this also does, it causes a so when you have sharp pulsing during the charging, it also causes a rush of these magnetic particles and they produce a number one, motion of the device towards the positive electrode, so the whole device lifts up, and also because of the shape, it causes a high concentration of particles below the craft. In this area there's lower density of these particles. It also produces a corona wind as well, downwards, which also contributes to the lift. But there definitely is a electrogravitic effect that happens there as well. But we'll get into that later on. For now, let's focus on how do we get anti-gravity. Okay, so I guess I digressed a little bit, but I just want to give you more background in terms of how how gravity can be affected by these magnetic particles. And in fact, the gravity particles are essentially magnetic particles. And just to reiterate the difference between the magnet particle or the magnets and gravity. If you have a magnet, right, the magnet is sitting in a sea of this gravity particles or magnetic particles. So you can equate this to having a device or a series of pumps, or a device with a series of pumps sitting maybe a mile under the ocean. So you have enormous pressure onto this device, and then if you turn on these pumps and they all point in the same direction, the typical flow is not far from this device because of the pressure. So the water then would get sucked in from the ocean, and as the water shoots out, they don't go far, they slow down and then curve back and then get sucked in along with the rest of the ocean. So that is how the magnet will also operate within within the background sea of magnetic particles. Okay. Alright, so in the next video, we'll go through the exact mechanism of how we'd what is the mechanism of getting or expelling the magnetic particles from that metal. So hopefully it will be a shorter video.